The true root cause of a broken part is never the physical failure itself. It is the flaw in the system that allowed the part to fail in the first place. Take a look at this CAD wireframe of a battery mounting bracket. During a 50,000-kilometer durability test, a crack appeared right near the mounting flange. We mapped this out using the 5W1H framework: what happened, where, when, and the severity, pinning these details directly to the fracture point. But basic details are insufficient. We need hard data. We track the exact torque values, material thickness, and the specific vibration frequencies the bracket was exposed to. We never assume why it broke. We document the measurable facts. Skipping this step guarantees the engineering team will waste weeks solving the wrong problem. This Pareto chart categorizes our failure types. Out of all anomalies, there is an 80% statistical spike strictly at the weld area and mounting flange. This visualization eliminates the vast majority of variables. The team now has one precise physical location to investigate. This fishbone diagram brainstorms variables affecting that 80% failure point. It maps the 6M categories alongside a dedicated branch for design. Mapping these side by side prevents premature conclusions. Zooming into design parameters reveals specific subcauses like sharp corner radius and fatigue strength. These tools do not solve the problem. They filter the systemic noise, giving a clear target. This vertical 5Y flowchart allows us to drill straight down through the variables we identified. We start with the physical evidence. The bracket cracked due to a high stress concentration, and that was caused by a sharp 2 mm bend radius. Pause the video and trace the final 2 steps yourself. What systemic flaw would allow a sharp bend radius to reach production? The engineer used an outdated design standard because the company lacked a mandatory design review checklist. To prove our 6 mm fix digitally, these side-by-side CAE stress plots compare the original 2 mm bracket, glowing red with high stress, against the 6 mm bracket in the low-stress blue zone. To validate physically, this DOE matrix cross-references material thicknesses against bend radii before authorizing new parts. Rounding off the physical bend radius is a temporary patch. Implementing the missing review checklist vaccinates the engineering process against future recurrence. This is a DFMEA table, used during the risk assessment phase. We use it to verify that fixing the bracket doesn't accidentally introduce new issues, like excess vehicle weight or new vibration modes. Once cleared, the redesigned bracket must successfully pass final physical validation, enduring strict durability testing and thermal cycling. The validated physical fix is permanently written into the organization's engineering standards. The new rule requires the minimum bend radius to equal at least 3 times the material thickness. We map this entire journey onto this 8D problem-solving flowchart. Our Pareto and Fishbone diagrams drop into the problem description phase, while 5Y analysis anchors the root cause. This 8D framework structures these disparate tools into a cohesive timeline, dictating exactly when to collect data, apply quality methods, and execute validation. Effective root cause analysis converts a single field failure into permanent organization-wide intelligence.